Okay, so we're on lecture 25, actually. Okay, so for review, on lecture 23, we went over trans conductance and also trans resistance. We also looked at the two-port representation um, of a NPN transistor right here, and looked at the Y parameters, and found out that we can convert this to a hybrid pi model by assuming that this G mu right here is 0. So your voltage controlled current source is no longer there, right? Okay. And also you could simplify this too by eliminating your output resistance right here. So if you eliminate that right there, then you have an even a more simple model. We also looked at the James Early voltage right here. If you extract all these out, they become VA. And from that, we were able to get the intrinsic voltage gain, which is your early voltage over your thermal voltage, which was equal to 40. It's supposed to be 40. Yeah. So this right here is 1 over 40, right? So that's why the 40 is right there. 40 times your early voltage. And this was a graphical representation of what the transconductance looks like. So the transconductance of a transistor right here is GM, that's the slope right here. And this VB is the small signal variation about that Q point right there. Then in lecture 24, we did this correction right here on our conceptual understanding of the DC blocker. So it's a DC current blocker, not just any old DC blocker, and also an AC current bypass. So what you can do is you could think of this AC component right here bypassing this resistor going around this direction, or think of it as it blocking your DC from going this direction, so your DC only goes that direction. So what happens is that your total current, your DC plus your AC, sort of like splits up right here, where the DC goes this direction and the AC goes that direction once you get to steady state. Of course, when you're building up the steady state, that DC right here is going both directions, right? Until that is saturated totally with the voltage, right? Which is C times the derivative of voltage. Okay. Also, if you want to get the voltage out of that, instead of just looking at the current, then you send your voltage, your current through a transimpedance amplifier, and then that's a way to convert your current to a voltage for either AC or DC. We also looked at hybrid pi in terms of voltage-controlled current source or the current-controlled current source. Either you could do it this way or this way, and the difference between these is that this is the transconductance times VBE, which is that voltage right there, and this right here is beta 0 times IB, which is right here. So they're controlled. This is controlled by current. That's controlled by the voltage. And here's that simplified hybrid model where you got rid of that RO right here, the output resistance. This is the BJT model right here. A variation of that. And this right here is the terminal voltage and input resistance is what we left off on. And then we'll continue on that with this lecture. Okay. So here are the concepts we're going to cover today, all the subsections. We're going to look at signal source voltage gain and look at the limits and model simplifications. We're going to look at a design guide for the common emitter amplifier. We're going to look at the upper bound of the common emitter gain and small signal limit for the common emitter amplifier. Small signal models for the FET, small signal models for the MOSFET, intrinsic voltage gain for the MOSFET, and definition of the small gain operation for the MOSFET, and small signal model for the N and PMOS transistor, and small signal model for the JFET. Okay, so for this right here, the signal source voltage gain, So this continuing on where we left off. And so remember last time we left off with this terminal voltage, which is this ACE-VT, which is V out over VB. So that's circled in red. So here's V out of the transistor, and here's VB. That's what this ratio is. And it's the terminal voltage gain right here from that terminal right here. Okay? And we found that that is negative transconductance times the load. And that's negative, so it's 180 degrees out of phase. It's an inverter. And then we also looked at the input resistance, this RIB, which is the ratio of VB over IB. Okay, so this is sort of like the resistance seen from looking in this direction. And the overall current right here is IB, and that's going in this direction. Okay, so this is just a simplification of that. So this is this current IB going in this direction. And this VB right here is the voltage right here, but you could simplify it by saying, well, let's just apply that voltage, that same voltage to that one. You're going to apply this voltage right here. Okay, so that's what this is. And this RIB, it isn't explicitly seen here, but it's the resistance seen by looking at it. So that's why this RIB just equals this R pi right there. So the overall voltage gain, V, is this right here. So it's the output over the input, okay? But you have this intermediate gain right here. So what you could say, well, this output over input, you could break this up. These two right here become these two, and then you insert this VB right here on the numerator and denominator right there. And so this part right here is what we've seen above, right? This is just VO right here over VB, that V over VB. And that's what that is. So we got that from up there. For this right here, well, VB right here, if you do voltage division, it is this resistance right here over the sum. Okay, so you could think of it like this. Now remember, we said that RIB is really equal to R pi. Okay, so this voltage at this branch right here, this voltage right here, is these two in parallel, right, which is right here, over this in series with these two in parallel, right there. And you're starting at this voltage going down that direction. Okay, so if you just take the ratio or just plug this into there, the VI's cancel out, and that's where you're getting this from. And this other part right here is coming from this, right here. Okay, and also from voltage division, you know that this right here is going to be less than 1. Okay, but you're multiplying it by this, and this could be quite large. All right, so now let's look at the limits and model simplifications. Okay, so let's look at the limits to the voltage gain of the common emitter amplifier. So we're going to take it as this right here, and I put this on the side right here just to show you where all this came from. Remember, this is AC analysis, so that means that these capacitors become blockers, right, for DC current. That's a blocker for DC current, but also for the AC current, this also becomes a bypass. These are all AC bypasses. So it becomes a short circuit for the AC bypass, and this is also a short circuit for AP bypass, so it totally eliminates RE. So remember what we did last time when we do our AC analysis, this part right here becomes just a short circuit to ground, right? And also remember when we do our AC analysis that any constant voltage, any DC voltage, becomes a virtual ground, or just becomes a ground. So that's why this part right here becomes a ground. So this resistor R1 is actually in parallel with R2 going to ground, because that's going to ground, and that's also going to ground. So that's where you get this from, where this R1 is in parallel to R2. And for the load right here, instead of the load just being this R3, we're going to take the load as all these guys, right? Because they're all in parallel, they're all at the same voltage. So it's R3 is RC, and is R0. Okay, they're all in parallel, and they're crossing the same voltage. So you're going to call that whole thing RL. And so that's why this last simplification, where all this just becomes RL, and yeah, and this doesn't change over here. Okay, so with that, this is what we had from last time, this right here. Now, what we can do, okay, so what we can do, we can assume this Ri is much, much less than these two guys in parallel, right? I'm talking about these two guys right here. So this is going to be much, much smaller than these two in parallel. So if that's the case, then what we can say is this. Let me think for a second. I'll come back to that. Okay, so here's what we can get for the upper bound. So remember, this right here is going to be the load resistance, okay? And this right here is a transconductance, right here, the GM, and this negative is 180 degrees phase shift, okay? So that just corresponds to this right here. So you have this RL, and you have this GM right here, the transconductance. And so this right here is sort of the model, like if you want to inspect a transistor and then look at what is the upper bound for AC analysis, the model looks like this right here. It's very simple. Okay, so, and that's as best as it can get for that, for the upper bound. Now, so for this right here, since this Ri right here is much, much less than this, then this value right here becomes insignificant. Well, I mean, the sum of this, the contribution of this to the sum becomes insignificant. So basically, the denominator is just this right here. And this thing right here is the same in the numerator, so the whole thing becomes 1. And so this whole thing just becomes your transconductance times your load. And your load right here, remember, it's all of these in series. Okay, that's what this means. I'm sorry, all of these in parallel. So that's what this is. Your RO, your RC, and your R3. Okay, that's the real load, right? But you're assuming the whole thing together, looking at your AC version, all of these right here are in parallel. And that's your entire load. Okay, so now let's look at designing around that, okay? So for most amplifier designs, RO is usually much, much less than RC, okay? So that's this right here. So this resistor is usually much, much less than RC. And you'd like to have R3 to be much, much less than RC. And that's your load, like your real load. So you like to have this much, much less than that. So really, this resistor right here is larger than both of those. That's the goal there. Okay, so if that's not the case, then the load, if that is the case, then the load resistance on the collector node, which is this node C right here, is approximately RC. Okay, so this right here, this RL, the entire load, becomes this RC right here. And then this GM, the transconductance, is defined as this IC over the thermal voltage, right? That's where this comes from, okay? And so this, passing a current through this RC is basically the voltage of your output right there. And that voltage of your output is some fraction of your VCC right here, okay? And this Greek letter, is it chi? SI? Anybody remember that? No fraternities, sororities? Okay. This Greek letter is in between 0 and 1. Okay, that's the range. Your thermal voltage is 1 over 40. Okay, or 25 millivolts. Okay, and so by plugging this value right here into that, and this right here into that, you get this for your overall gain of your transistor, which is this over that. And so it's going to be negative 40 Greek letter VCC. Okay. Now this component right here, this little parameter between 0 and 1, is usually taken as 1/3. Okay. So basically, you could think of it as for many designs is allocating 1/3 of your power supply. Okay, across your RC, which is, you like it to be your largest. So that could be like negative 13 VCC if you plug in 1/3 right there. Now, to account for other approximations you made along the way, because you made a lot of approximations to go from here down to there, you can have even a more conservative value and just say is negative 10 instead of negative 13 times VCC. Okay. Now that is like, a rule of thumb right here. And now if you have dual power supplies, then instead of having VCC, it's your VCC plus your VEE times negative 10. Okay, so what this really means is that you only really need to know your supply voltage to make a really good, well, a pretty rough estimate of your common emitter amplifier. So if you just know this or that, or both of them, you multiply that by negative 10, and that's going to be a good approximation of what your gain is going to be. Okay. And as an example, if your common emitter amplifier has like a 10-volt supply up here, then you expect to produce a gain of about 100 or 40 dB. Okay, so now if we let RC and R3, this is really bad typing. If both of these are much, much greater than R0, then we can achieve the most gain from the transistor by saying this right here. Okay, so and this is going to be your intrinsic gain. So your intrinsic gain is just your transconductance times RO. Okay, for both of those in parallel being much greater than RO. And the book also says for the highest value, well, for these a typical value for these gains right here, this intrinsic gain is 40 times the early voltage, and it's on the order of about 1,000. Typically. Okay, so small signal limit. So first let's recall that for small signal operation, and that means you're in the linear regime, right? The base emitter voltage, VBE, across pi, this R pi, it must be less than 5 millivolts. Okay, that's that right there. Okay, so if that's the case, we're going to plug in the 5 milli right here, and that means your voltage input has to be less than or equal to this right here. Okay, and so that's for your small signal limit to be in a linear regime. You can put in more, but then it becomes nonlinear after that. And that's for your input voltage. Okay, so let's look at the small signal model for the MOSFET. Okay, so here's the MOSFET right here, and here's the small signal model of that. And here are the Y parameters. Okay, and remember this right here, gain to source, And remember, if everything is capital, it's the DC, and that sets the bias, or the cue point. If everything's small, that's the small perturbation, the small signal, AC. And the small and the capital together, that's the total. So you have your VGS, your VDS, IDS, and IG, okay, corresponding to these things up here. Okay, so like last time for the BJT, what we can do is look at these parameters right here, and then do our partial differentiations applied at the cue point. Okay, so if we did that and we plug these values in for ID, VDS, IG, and this Kn. So what these values are, the Kn is a transconductance parameter. The VOX is a capacitance per unit area around, about the oxide. This mu n is the electron mobility. W that you see is the channel width. L is the channel length. VTN is the threshold voltage for the formation of the inversion layer, and lambda is a channel length modulation parameter. And it ranges between 0 to 0.2 per volt. Okay, so that's what you're going to plug in here into your Y parameters to find out what they are. And in doing that, you get this right here. Okay, so these two are, of course, 0 because that's 0, right? The transconductance, the GM and G0, that's what these expressions are right here. If you plug those in and do the differentiation. And okay, so from that alone right there, we can see our MOSFET model. The transconductance is this right here, right? We get from that. And the output resistance, RO, is this. And that's what we get from this. Here's the conductance. So inverting that, you get your output resistance right there. And to compare that to the BJT, remember this is what we got last time in a previous lecture for BJT, for transconductance. And you can compare that to this. And for the output resistance, you can compare this right here to that. Okay. And also for the intrinsic voltage, the intrinsic gain, here's what we get for the MOSFET right here for intrinsic gain. Okay, and for BJT, we got this right here. So it's quite different. And to look at that in terms of numbers, and this is actually important if you're trying to design certain things, right? So so it says here for the intrinsic voltage gain for the MOSFET, so mu f decreases as the operating current ID increases. So the larger the operating current VD for the MOSFET, the smaller the voltage gain capability, which is kind of interesting. However, the intrinsic gain for the BJT is independent of the operating point. And you can see that here, right? So as these values go from 1 microamp to 1 milliamp, you see the intrinsic gain as decreasing right here. But as these go over the same range from 1 microamp to 10 milliamps, you see right here the intrinsic gain is constant. Okay, so that's something you want to consider if you're going to design and you're trying to decide if you're going to use a MOSFET or a BJT. Okay, another thing you want to keep in mind is this right here. Look at R pi. This right here is, so R pi is huge, always, right here. Here, it's kind of large, mega ohm, but down to ohm right here, depending on your current coming in. Okay. And these values are pretty much similar right here. Okay, so let's look at this, what the definition of a small signal, what small signal is for the MOSFET. Okay, so so the limit of small signal is limited by the linear operating range, of course. Okay, so using the simplified drain current expression, where lambda is 0 for the MOSFET, we have this right here. Okay, so this is what we got from our last slide. Okay, now what we can do is we can replace the total drain current with this, the DC plus AC. So if we plug that into here, and then right here the gate source voltage, replace that with the DC plus AC, then we get this expression right here. Okay. So this right here, it was just this being plugged in. And that right there is just that being plugged in right there. Okay, so what you can look at is this right here, which is DC, and these right here are also DC. Okay, this right here varies with your small signal. Okay, same with that. So these two, so this piece right here is the same as this piece. So they're equal, so you can get rid of that. And then what you're just left with is this ID times this right here factored into this expression over here. Okay. So from that right there, you know for linearity, this ID right here must be directly proportional to this VGS. Okay, so that means that this term right here is really small compared to this term. Okay, this one's negligible. So for this condition right here. Okay, so again, in this book, they use a factor of 10 to mean, you know, much, much less than or much, much greater than. It's like an order of magnitude, increase or decrease. So with that said, then what we can do is we can apply this to that. And so that means if we're going to take this and reduce it by order of magnitude, we get this. So instead of saying that this is much, much less than that, we're just going to say that this is less than or equal to this right here, which is 0.2 times the difference between that. Now this, for the MOSFET, this difference right here can be several volts. Okay, and that is a comparison to the BJT, where you have the VBE here, and that could only be 5 millivolts. Okay, so when it comes to design, that's something else to consider, right? So that VBE for BJT is 5 millivolts, but this could be several volts. Okay, so you have a much larger range for your VGS than for the MOSFET's version. Okay, so in terms of looking at the change in drain current that corresponds to a small signal operation, so the small signal right here over the DC, which is GM VGS over ID. Okay, so that's like 20%, and this is like 40% right here. So what this really means is that, what I wrote right here, so a 20% change in this right here in this VGS corresponds to a 40% change in the drain and current, in the source currents from the Q points. Okay, and we did the same thing with the BJTs as well. Okay, so now let's look at the small signal model for the P and the NMOS. Okay, so the small signal model for PMOS transistor, it actually equals that of the NMOS transistor. It is very similar to what we saw last time with the NPN and the PNP. Same kind of idea. Okay, so okay, so in both cases here, so here's NMOS right here, and here's the PMOS. Okay, so they both have this DC, right, and they both have this small signal being added onto that in series. So this right here is like this, except this is inverted over here. Okay, but for small signal analysis, what you're really concerned about is this, not really that. You're concerned about this, not the bias. Okay, and you're also concerned about ID. Okay, that's what you're also concerned about. So even though this current right here is very different than over here, like this is going out, this is going in, and this is like the gate to source. Here's the source to gate. SG versus the VG. So for NMOS, we have this. Okay, so the gate to source voltage, VGS, is equal to your DC plus your small signal. And very similar for the current. And for the PMOS, this voltage source to gate is equal to VGG minus your small signal. Okay, so what this means is this, that if this value increases, then this value increases. Now, if that increases, then that must increase, right? Now, if this stays the same, the only way for it to increase is if that increases. Okay? Now, let's apply that to this right here. If this increases, then that decreases, right? Like if because assuming this is constant, if your small signal is increasing, then that will decrease, right? Because you're subtracting it. And that decreases, that decreases. And if that decreases, if that's constant, then that means that had to increase. So remember, on both cases, if both of these increase, both of these will also increase. Okay? And that's why they're identical for small signal. Okay? And so you can look at this as this right here, okay, where this right here shows the small signal plus the large the DC, okay, and all of these right here. But this right here is your small signal version of it, where you're just looking at small signals everywhere, okay, small AC signals, and that's what this corresponds to. And if you're only looking at small signals, they look exactly identical. And because of that, you're going to use the same identical mathematical model to represent the small signal. And so that's going to be this right here. So here's your model for a small signal, and it corresponds to both NMOS and also PMOS. All right, so let's look at the JFET. So the drain current for the junction field effect transistor, the JFET, and the MOSFET, they can be written in a similar form. So this is what we have for the JFET. And to remind you guys from your previous class on this, what these mean. So the IDSS is the saturation current. The VP is the pinch off voltage, and lambda is the channel length modulation parameter. Okay. The total gate current IG is the current of the gate to channel diode, which is expressed in terms of the gate to source voltage, VGS, and saturation current, IG. So it's expressed like this. Okay. Now, of course, this is assuming that you guys remember it from Digitron. Of course, well, most of the stuff does. So here's the schematic of that right there. And so applying these two relations to the wire parameters as before, as we did on all the other ones, this is what we get for the G pi, the G mu, the GM right here. And it says here, because the JFET is normally operated with the gate junction reverse biased, right here where the IG is negative ISG, we're going to have this R pi be infinity because of that. So this right here will cancel. So you have zero conductance, which means infinite resistance for the R pi. Okay. And so just to compare the intrinsic voltage gains, this is what we get for the intrinsic voltage gain for the JFET right here. And remember, this is what we get for the intrinsic voltage gain for the MOSFET right here. And as you can see, they are pretty similar, right, in form. They both have the IDs, right? They both have lambdas right here, but this has the pinch-off voltage right here, and this has the Kn, and it has the IDSS. So they're sort of similar in that respect. Okay. Any questions about this stuff? All right, great. Okay, so that's it for today, and see you guys on Friday. And also remember, this weekend we'll have our practice exam. Huh? What time? Oh, yeah, we're going to decide on the time on Friday. Yeah. And also, if we even have it on Sunday, we could have it on Saturday, but I think Sunday might be. Yeah, we'll see.